All right, what is good, everybody? It's been a while since I've done a screencast like this. If you don't know, there's a Codeforces round happening in about 10 seconds. It's a Div 2, so um, I want to be somewhat casual. And other than that, let's just, if you're competing, good luck. And we're going to get right into the problems. Given a multiset, determine if you can split it into exactly n pairs so that the sum of the two elements in each pair is odd. I think it's just checking to see if there's n odd numbers. So if n is an array, or I guess 2 times n times 2. If sum is equal to n, then it's possible, otherwise it's not. Alright, let's test this really quickly. Okay, and submit. Exactly at 1 minute mark. Dang it, we could have gotten it under a minute. Whatever, it's fine. There's an infinite set generated as follows. 1 is in a set if x is in a set, x times a and x plus b both are in this set. Determine if n is in this set. Okay. So if x is in this set, x times a and x plus b are both in this set. So x times a plus b will always be in the set. So will x, so we can always take something. We could also multiply it again. So it's like, we want to check to see whether or not a certain value is in a set. Okay, there's 3 integers. I'll make everything a long, just in case. How close were we to first solve on this problem? We're just out of curiosity. Yeah, not even close. Sad. That's okay. We might have gotten first solve if we didn't run samples. Given positive integers, determine if n is in a set. Okay, well, it is indicated that b is slightly harder than normal, so I'll look at c just in case. Okay, given let f of I determine the minimal positive integer x such that x is not a divisor of I. We're going to sum up all of these. The minimum positive integer x such that x is not a divisor of I. Okay, that seems... I don't immediately know how to do that. I'll think about b then. Yeah, so like x, or if it's like ax squared, or it's something like, I guess, So if x in the set, x times a and x plus b are both in this set. Yeah, because even if we have like ax plus b, it's like ax plus 2b. Okay, so we can think of it as like we always multiply this ax's first. So like we do ax squared. Okay, I think I know how to do this. So if a is equal to 1, then we have to handle it a little bit differently. Because no matter what we do, the coefficient, we're always just multiplying it by 1, so it will never change. So then in that case, we just want to check to see whether if it's m mod b is equal to 1, then it should be possible, otherwise it's not. Okay, otherwise we do this, and then so while pow is less than or equal to n, yeah, and then pow, after every term we multiply it by a. Okay, so you've already multiplied it by a, and so if n minus pow mod b is equal to 0, then it should be possible. Let's give it a shot. Okay, this problem, you just read it along. We also have mod, so it's static final mod. Okay, so we have Is there a Q right now? There might be a Q. Whatever. I'll just open up D and E1. D looks, okay, it's also a mod. Okay. The minimum positive integer x, such that x is not a divisor of I. Okay, well, odd numbers, it's, for odd numbers, it should just be 2. It's just like 2 plus 3 plus 4 plus 3. Yeah, 2 plus, oh, wait, no, this is 3. Yeah. 2 plus 3 plus 2 plus 3. Will it always be a prime number? Well, is the first number, it's not divisible by always prime? Maybe not. I mean, if we cut out every, so like if we do n over 2, because all even numbers are divisible by 1, and then they're also divisible by 2. For odd numbers, the answer is going to be 2. Let me just write this down. Okay, so if x is odd, we do this, and then we reduce it down to just a bunch of even numbers. Because like we divide it by 2, and then it's just like the same thing. So we take a number, we divide it by 2, right, so this is just going to be equal to 4 plus n over 2. Yeah, so essentially it's just like we divide everything by 2, so instead it's 1 plus 2. Yeah, so we know that this is 4, and then if you do 1 plus 2, it's then we're looking at 3. Both of these are not divisible by 3. But if both of them aren't divisible by 3, what happens then? Oh shit, we got it wrong. Okay, I'll debug this. Oh, well, at least I'll think about it. Ah, frick, this is supposed to be 1. Oh, I'm stupid. Yeah, because like 1 is still a valid thing to check. Good God. Yeah, I'm very stupid. No, okay. Still not right. Is today going to be one of those contests? Let's see. Why is this not correct? That's the same as like adding it with a bunch of B's. So it's like a, and then a squared. Wait a minute. One times a is equal to 3. And like that's like a to the power of like p times x, which is like basically just 1. It's like a to the power of some p plus some multiple of y. So we have to check whether n is in this form or not. I guess if it's like no matter what, if it's a 1 and then like 4 and then 28, it's always yes, because a 1 is already in the set. Yeah, because even if it's like x plus b, multiplying by a is like ax plus ab, which is like ax. Yeah, so it's like if we do a and then it's like, for example, if our current value is b plus 1, this is just the same as doing a plus ab. And so it's like a to the power of 1 plus b times some integer. So it's like always in that form anyway. Yeah, so it's like we can always just increase it by this power and then just check to see whether this integer multiple exists. I need a stress tester. I feel like this right here, I just don't understand why it's not working. Long equals math.random times, I'll just do 12. Alright, give me something. Are you kidding me? Really? 690. Okay, there we go. 13, 1, and 1. My thing prints. No. But apparently it should print yes. Oh, because we can just increase everything by 1 over here. Oh my god, is that the... Wait, is that like a special case? If b is equal to 1, then it's always possible? Oh my god. That's... Oh my god. If b is equal to 1, it's always possible. I guess that makes sense. Let me just stress test this a little bit more. Okay, I'm gonna submit this. Alright, I'm gonna think about C now. X is not a divisor of I. So if a number isn't 2 or 3 or 4, pretest 4, pretest 5, pretest 6. Yeah, okay, we got B, finally. That took a little too long. Yeah, stress tester for the win. Wait, so if it's 2 times 3 times... I wonder what the smallest an answer could be. Like, X is not a divisor of I. So what is like the LCM? Yeah, I guess we could use LCM to figure something out. Because if every number is at most 10 to the 6, then GCD of itself and V. Temp, you multiply itself by V and then you divide it by its GCD. If temp is strictly greater than 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then we'll just print V and we'll break. So this is a first divisor. Yeah, so like, okay, it's at most 41. So f of I is at most, well, like 40, I guess. Okay, let's see a pattern, or like at least try to find a pattern. So we have something like this, and then D is equal to 2, D is also equal to V, D equals plus. And so if V mod D does not equal to 0, right, so it's like f of, I guess f of V equals D. Break. Stop and rerun. Okay, now I have a question. I'm curious about something. we do this 3 3 4 3 3 5 3 3 4 3 3 5 3 3 4 3 3 5. What about if it's greater than or equal to 4? Stop it and run. 4 5 4 5. Yeah, so for f of 6 is equal to 4. Four, 5, 4, 5, 4, and then 5. Or at least it's like it alternates between here and here. Yeah, because for 2, we cancel out all the numbers that are by 2. So I guess it's just like, if we can reduce it to, wait a minute, so when you multiplied, when the LCM of 1 through 41 is strictly greater than that, so that means it's still possible for it to be divisible by 1 through 40, but not 1 through 41. Is at most 41. Okay, so you can reduce the problem to this. So how do we do this step? Well, if we count f of x equals 2 is just how many odd numbers exist. F of x is equal to 3. We count how many numbers are divisible by 2 and 3. Are divisible by 2 but not by 3. And then we count how many numbers are divisible by 2 and 3, but not that. Okay, I think I know how to do it. Let's check. Long curves equal to 1 for v equals 2, v is less than or equal to 41, v plus plus. Yeah. So we need to figure out, for 1 through n, how many numbers are divisible by something. So for example, how many numbers are divisible? I want to figure out how many numbers are all divisible by cur times v divided by the GCD of cur and v. Yeah. So we have to count how many numbers are divisible by this LCM. Minus, well, okay. So long temp is how many numbers are divisible by cur itself, like previous LCM. If there were all numbers from 1 to n, then if there are n numbers, yeah, if there's n numbers, then it's like n over, I think it's n over cur. Yeah, because even if it's like 10 over 3, 9 over 3, 8 over 3 would still be 2. And then temp, you subtract from this n over LCM. So now this includes all numbers are divisible by cur, but not divisible by v. So we have to mod this, and then res temp times v mod. And then of course we mod res as well. That's not right. Oh, I'm not updating cur should equal to LCM. Alright, let's see if this is right or not. 420 solves. Can we be the 421st? Pretest 4. Okay, we got C. Good. We had a rough start, but we're not doing too bad anymore. We're given a sequence A where its elements are either in the form plus x or minus, where x is an integer. For such a sequence X where its elements are either of a form plus x, wait, what does this operation mean? Plus x or minus? For such a sequence S where its elements are either in the form plus x or minus, define f of s as follows. Oh, okay, we have operations that look like that. I see. Iterate through the elements of S from the first to the last and maintain a multiset. For each element, if it's in form plus x, add x to t. Otherwise, erase the smallest element from t. After iterating through all S's elements, compute the sum of all elements in T, where f of s is defined as a sum. The sequence B is a subsequence of the sequence A if B can be derived from A by removing 0 or more elements without changing the order of the remaining elements. Okay, so for all subsequences of A, we want to figure out the sum of all these values. Okay, we have also a mod over here. If it's in the form of plus x, add x to t, otherwise we will erase the smallest element from t. If t is empty, you just skip a step. Okay, so if it's empty, then it's 0. If it's all minuses, then it's just 0. We add it by this integer. If we ignore the subtracting component, so instead of so if we replace a minus sign with just add 0, or if we just don't do anything, then the way we can solve this problem is we can just find the contribution of each number. So for that number, how many times does it appear in a set? Yeah. But now, if we have this number, it's for each x numbers that we loop through, we want to first count when for each thing. If we assume it's the smallest element, for example, then it can get disabled here. But if it gets disabled here, then it's there has to be some element larger than it that we took over here, and then we got it disabled over here. And then it's something like that. Yeah, so it's we have some set of choices, basically. So if we visualize it like this, for each element, so we do that, we have plus x, and we have some bucket of operations, and then a minus sign. Some bucket of operations and a minus sign, some number of operations, a minus sign, something like this. I want to figure out if it can be deleted by this. All we do is make sure we add elements that are should be strictly greater than or equal to. I guess greater than or equal to is fine, because yeah, we can just say the tiebreaker is we just remove the element that's leftmost, and that should handle it, because then it's if we just remove this element, next time we process the same element, we only look towards the right, so it's fine. So all numbers greater than or equal to it, and then we remove x. Or we can pick up, if we want it to be disabled over here, then we have to pick up exactly one number greater than it over here, and then all numbers less than or equal to over here. If we want to pick something up over here, then we're going to need to take at least one over here. Yeah, so our choice is either we can take one in here and then here, or we can take two in here. Okay, so we just have a bunch of choices we could do. And no matter what kind of choice we make, we just need to count how many subsequences there are. So obviously, we take actually not necessarily previous elements, because we'll need to make sure that if this element isn't the first one in its block, we need to make sure we haven't taken any smaller elements. Yeah, and so instead, I'm going to figure out how many subsequences before here exist such that all the remaining elements are strictly bigger than it. Yeah, strictly bigger. I guess that makes sense. Um, there's only at most 500 different values of x that we care about. I'm going to think about this for a little bit. Yeah. Alright, I'm back. I had to quickly go to the bathroom. And while I was in the bathroom, I got to think about this a little bit. So I think I know how to do it now. 141 solves or I know, 100-ish. Yeah, I think it's fine. We just need to carefully implement this. Where we have n and then we have a bunch of operations. We do this, otherwise we'll just set it equal to -1. So we do DP at like basically among this prefix I. Number of ways to choose elements such that how much memory do we have? Okay, that's fine. Erase the smallest element from T. Yeah, so we can just figure out among all possible subsets that include this element, how many of them actually contain the element at the end. That's our goal. Okay, so we do like log n. I guess it's at most this many. That could be part of it. So if we include the first element or we don't include the first element, like dp at 0. If we do the first element and we don't pick up anything, that's one way we could do the subsequence. Or if we do more like a sum of valid ways. Yeah, because not including an element will just make it 0, and then if Okay, how do we work out these details? Okay, so when we have multiple of the same element, we always remove the leftmost one. So that's our tiebreaker. Okay, so basically, contributes to the answer. Yeah, the implementation is kind of weird. But then if we take if it's less than or equal to focus at now if we take the element itself, okay, so we have to take this element. So it's like if we took one element, that's just equal to this, because we always take a focus, and once we take a focus, it's basically considered to be a new smaller element. If array at 0 is strictly greater than 0 and focus is strictly greater than 0. Yeah, because if it's a minus sign, then like the sum of it over all subsequences. Well, I mean, multiplicity. Oh. dp at n-1 is the sum of all those in general. So if array at 0 is strictly greater than 0, and the focus is strictly greater than 0. Array at 0 is less than. Because I guess we should account for how many ways. Oh, I'm so dumb. It's not sum of number of ways. It's still like number of valid ways. Because we're counting contribution. We want to count how many times something appears. Yeah, I'm being stupid. Okay. So dp at 0, 0. There is exactly one way to do that. And it's equal to 2, because no matter if we take it or we don't, or I guess, wait. Okay, focus is equal to 0, then dp at 1 is equal to 1. Okay, so if array at 0 is equal to -1, so if it's a blank space, then no matter if we take it or not, we can either take it or not, it doesn't really matter, so there's two ways to do it. Otherwise, we know that array at 0 is a valid number. So if array at 0, if it's a number that takes precedence over it, so if it's less than or equal to array at focus, then dp at 0 at 1. dp at 0, 0. Because if we took this element, it's going to be greater than it, so it's essentially the same as doing nothing. Yeah. Okay, and so after we do this, this should tell me how many subsequences. dp at n-1 at v. If array at t, if it's equal to -1, then it's just everything's just a gap. Like dp at t at I is just equal to dp at t minus 1 at I. Yeah. Or I guess we have to subtract an element from it. Or, it depends on whether it appears before or after as well. Because if it appears before, and we take away elements that don't exist, then it's okay. But once it appears after, we can't do anything about it. So if it's, okay, so if we're adding this element, in the number of ways, then like we essentially remove a min. Yeah. And then, okay, if t is less than focus, then it's fine. I mean, it doesn't really matter. It's like, even if we remove like t and then 0, plus equal to dp at t minus 1 at 0. And then it's like if dp at t at 0 is greater than or equal to mod. Yeah, that's fine. It's just we remove an element. So else. So if t is less than focus, else if t is equal to focus, else. We have 3 different cases to follow. The first case, what did the first case do? Does 4, or yes, yeah, if it's less than focus, then if array at t, if it's less than or equal to array at focus, then it can be taken before it. Else if t is equal to focus, that's something else. If it's like this, then array at t has to be strictly less than array at focus. Yeah. Okay. How do we do this dp? I mean, no matter if we include it or we don't include it. Okay, so this is if we include, it's like we include this thing into our subsequence or we exclude it. It's pretty much the same thing. It's just where it's like dp at t at I. Yeah, and this one's already added because like even if you're included, it does the same thing. T minus 1 at I if dp at t at I is greater than mod. There we go. Array at t is, okay, so if we do this, okay, well, no matter what this element is, if we exclude it, it's always the same thing. So if we exclude, it will always be dp at t at I. Yeah, like its attributes will just stay the same. dp at t at I less than equal to mod. Yeah, it's like over here. But in this case, we have to include it. Must include. Yeah, include. Exclude. So if this is less than this, then we add on an element. Okay, so then it's like dp at t at I, dp at t minus 1 I minus 1. If dp at t at I is greater than equal to mod. Okay. Yeah, so this is like if we included this value. Otherwise, if we include this value, then essentially nothing has changed. So we just do that. I think that's legit. Yeah, and then include, we do this. Because like we gain one like buffer element. And if we don't get a buffer element, then it's just like nothing changes. Okay, the last step is over here. Must include. Yeah, so we consider it as like an element greater than that. Yeah, so this is so you consider this as like adding an element. We do this. Let's take a look. Why not? Oh, I'm not doing this DP correctly. Hold on. Or like I'm not adding it on correctly. So we do temp. Yeah, because we have to first figure out how many ways exist, and then temp times or the actual value itself. Um, 16 and some big number that starts with 750. Nope. Oh. It's not quite correct. So you have to debug this. You just delete one of them. Let's see. What is happening here? Like what happens if we just do? Oh yeah, obviously that's 0. We do 2 and then it's like minus. Oh wait. Is that just 69 times 2? Yeah, it is. Okay. Yeah, because like we have to take this element and then we also have to not take this element. What if a focus is just one element? Yeah, it's fine. What if it's like... Yeah. Okay, what do we do here? Yeah, even if we include this element, it doesn't contribute to that. So it's t and then t minus 1. If we have to include this element. Okay. Array at t is less than array of focus. And we start from 1. Yeah, because by taking this element, we don't, by putting it in front, we'll create that. Otherwise, okay, well, if focus is equal to okay, I gave 9,641 different ways to do it. I guess it's actually not obvious. N minus 1, and there has to be at least one element remaining. Oh, wait, but we have to make sure that it never dips below 0. Yeah. Make sure we never go down to 0. So it's like, because once we get a 1, we have to stay at 1. Otherwise, if it becomes 0 at some point, then that element got removed. So it's like if I is equal to 2, yeah, because if it's at 1, then it's like we gained an element from this. But we can only gain elements from 2. If we don't do anything, then we can just let this stay as is. And then over here, if we don't include, okay, so if we include a useless element, or if we don't include the element in general, it does the same thing. Okay, let's try this. See if this helps any. Okay. Let me just try the first sample. Let's submit. Pretest 1. Time limit? Time limit might be a little tight, but the bounds are pretty generous. Pretest 13. Pretest 14. Pretest 15. Pretest 16. Pretest 17, 18. Still 18, 19. Okay, we got D. 1590, 3-second time limit. That's fine. I don't think it's a problem. Okay, let's go to problem E, or I guess E1. Yeah. This is an easy version of a problem. The only difference between the easy version and the hard version is the constraints on N. You may only make hacks if both versions are solved. Okay, well that's pretty standard. Like, text. I don't know why I had to look at that. Okay. Permutation of 1 through N. Okay. Yeah. Number of versions of the permutation. Yeah. Let P and Q be 2 permutations of size N. Find the number of permutation pairs such that P is lexicographically smaller and the number of versions as P is greater. Huh. Interesting. Mod might not be a prime. Okay, well, one trick we could do is if we just ignore this condition, the lexicographically smaller condition, and we just have to count how many pairs of inversions exist such that one is greater than the other. I mean, well, we would also have to determine. Yeah, okay. Maybe not. And n is at most 50. So how are we going to solve this then? Mod might not be a prime. Okay, so what if we build these permutations like one by one? Could we calculate contribution every time we add an element in? Because if it's something like I guess if it's something like dp at a and b and like some other stuff if needed. ABI, for example. How many inversions would I currently have? Or like P and Q? The maximum number of inversions is about I squared. So it's like, if we do the delta of inversions, then that could be up to I squared. So this would be like, what? 50 to the power of 5? Does that even run in time? It does. Okay, interesting. P inversions minus Q inversions. Maybe something like that. Okay, log m equals long. I guess mod. Okay. Make hacks only when both are solved. Okay, so score distribution tells us that D is about as hard as E. So if I guess if we have something like if we put in the 2, then we know that this will contribute. Oh, but we don't know which element it's in. Can't really use a bit mask either. Okay, so we look at, okay, if we put the ones at some point, then the contribution of inversions is fixed. And then it just turns into just how many ways I do it in general. Okay, so it's like if we put both ones, if ones are like both the first position, then we just need to solve the answer on n-1. If ones are at a different position, then that means, for example, if we assume like 1 is here and then here, or I guess it depends on what element we put in here. Yeah, because once we put an element in, it's just the same problem on a n-1 version. So in here, it's like if we put this element and this element, well, we need to make sure that okay, if the element we put is equal, yeah, I think the fact that it's a permutation is important. So we're moving one number. Size n-1. Do dp at given a permutation of size n, the p inversion minus q inversions. We have to process n elements, count how many of these exist. That's already n-cubed memory. And we have to make sure that once we put like n elements, yeah, we'll need to keep track of whether it's like already satisfied or not. Yeah, so there's this many states. Yeah, I think the fact that there's this many states will never change. It's just that the transitions will be a little bit trickier. Okay, I'm gonna try this because I think I can feasibly do this in 28 minutes. But how are we going to do this? It's n times n-1 over 2, so it's like 50 times 49. I guess it's 25 times 49. 1,225. So we can either do it as negative or positive. I guess static final int shift is equal to 1225. And we could do something like long dp equals new long. We do the first n elements. Among the first n elements, we do like shift times 2 plus like a little buffer value. And then we do, yeah, because we want to do that's like negative. Yeah, and then we do 2. What is 50? It's not a big deal. Like dp at 0 at, okay, well, one element. So for int a is equal to 0, a is less than n a plus plus. For int b is equal to a, b is less than n b plus plus. Okay. So we do dp at some value in here. So like we do dp at a at b. Okay, so inv a is equal to okay, if we put down a 1, it's equal to I mean, it's just equal to a, right? Because if we put down, like, if n is equal to 5 and put down a 4, then we've created 4 inversions. Like a minus b plus shift dp at a, no, dp at 0 at delta, and tag is equal to, okay, if a is equal to b, then this is equal to 0, otherwise it's equal to 1. Tag plus equal to, I mean, there's exactly one way to do this, yeah. Because like even if the same delta and the same tag, it could still, yeah, okay. So for int t equals 1, t is less than n, t plus long rise is equal to 0. I first establish what a result needs to take. It's just for int, wait, the number of versions is p is greater than the number of versions is q. Okay, so we don't count permutations that are just the same. Yeah, that are greater than the number of versions in q. So the delta is equal to 1. Shift dp at n minus 1 at delta plus shift 0. No, it has to be at 1 because it's lexicographically smaller. Okay. And then for these values, okay, so for int matching permutation, or no, if it's like, okay, if they're all 0, that means they've so far been the same permutation. So if so far they've been the same permutation, then we have to figure out an easier way to subtract. Or that's not necessarily an easier way, just like, if among these n elements, if an offset already occurred, it doesn't really matter what else we add. Yeah. So go from non-offset. We go from dp at t minus 1 at 0. So for int a is equal to, for int d is equal to 0, d is less than or equal to, I guess 2 times shift? No, just shift. For int a is equal to 0, a is less than n minus t, a plus plus. For int b is equal to a, b is less than n minus t, b plus plus. Delta is going to be equal to number of versions we add in here. It's a minus b plus shift. Yeah, and so it's like we just added on here, and so tag is equal to, if a is equal to b, then our tag is 0, otherwise it's equal to 1. So if d plus delta is less than dp at, as long as it's less than, as long as it can still fit, then we just add it on. And we do like dp at t, d plus delta at tag, dp at t from t minus 1 from d inversions, and our tag was 0. Yeah. So if, again, this mod, we just mod that. So this is we go from dp at t minus 1 at 1. And it's like the same thing, except tag is just always equal to 1. Is this it? Okay, wait, hold on. What is happening here? What is happening here? Oh wait, hold on. This is supposed to be 1. 1, 1, 1. That's strange. What is happening? Delta plus shift, and then it has to be strictly less than. Add on to mod. D is less than or equal to shift, D plus plus. Oh wait, is this, it's 2 times shift. That might be why. Yeah, let's try this. Still 0. That's not good. Let me try something. What does this give? It gives 10. Because like there's just that many ways to do it. It should be p minus q, so q should have greater many inversions. Yeah. What is happening? D plus delta. Okay, if it's 4 times 3 over 2 is 6. So there's at most, yeah, so in this case it's at most like 6. Or I guess we just say 7 just to be safe, but it's still 0. How many ways are there to do it? What if I do this? Debugging. Okay. Does this help us at all? The sum is 250. Why is that? Really? Really? Okay, so this is our current delta value. Oh, wait. This is not supposed to have shift. Yeah, because we've already shifted it before. Yeah. And d plus delta is at least 0. Let me try this. Let's try this again. Still 0. Why is it still 0? It's like dp, this is a current difference in inversions, and this is whether p is lexicographically smaller than q yet. Okay, so we loop over all choices of A and B that we have. Count how many inversions are created if we place this number next. N minus 1 and 1. Okay, so if A is equal to B, then this should give 0. Yeah, but like in here it doesn't matter because we've already made it so that it's guaranteed to be lexicographically smaller. dp at t, dp at d plus delta. I'm gonna make my own test case. If it's like 3 and a big ass number, it's obviously 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Okay, so lexicographically smaller. The number of inversions in P is greater than the number of inversions in Q. Okay, so what if I just did like 3 and like a big number? It's also giving 0. Okay, what if I just give like 2 and like a big number? Even that gives 0. Alright, we need to figure out what's going on. Okay. So DP at, wait, no, there's 1 and 2 and 2 and 1. Wait, no, yeah, 2 is always 0. 3. Are any of these lexicographically smaller and have strictly more inversions? This one has 2 inversions. This one has 2 inversions. This one has 1 inversion. This one has 1 inversion. Oh wait, actually, no. Oh yeah, this one has 1 inversion. Like, do we have one of these that have 2 inversions and 2 inversions? Okay, so maybe not 3 then. 1, 3, 4, 2. Okay, so we do number of versions created here 0, and then this is 1. EP at 0. Delta minus 1. No, I guess shift minus 1. What do we get for here? We get 3. Because like either 1, 2, 2, 3, or 3, 4. Okay, but once we get to 1, 2, 2, 3, or 3, 4, what happens over here? So we get this DP value. Wait, what if instead of I start from 0, and then I do like 2 times shift? So like I like just get everything. This should just equal to everything. 156. It is almost everything. Yeah. Okay. Is there anything equal to it? 156 is equal to it. Still 156. Shift. I wonder if we'll include how many permutations are just the same. I mean, it's not possible because of that. Yeah. Okay. Okay. B is equal to 0. Because once we get a value that's like offset like this, we just include any value that we want. Okay, I was just being stupid. 1, 2, 3, 0. Yeah, I was just being very stupid. Let's see. Can we clutch? Shoot, TLE. Okay, this is n to the power. This is like n to the power of 5. It might work if I convert to C++, but I don't know if I want to do that. Do we convert to C++? Or, dude. Is this something I want to do right now? What? Fuck it. I want to convert to C++. So. Because honestly, I honestly think we might be able to do it in time. Since it's literally just DP. I just need to copy, like, your template. C++ 17. Yeah, so I already do like this in NCN long. Okay, so like in NCN N and then LL. Do I already have defined? Yep, LL mod is LL mod CN mod. Int N CN N. How do I create an array? Constant max n is equal to. Okay, well, I guess I do long. One God. I have about 5 minutes to convert this to C++. I need to see wait, the 2D array in C++. I just want to look at the syntax for this. Like initialization. Okay, so it's like int. Okay, so it's LLDP where we do 51, where we'll do 2560. That's probably sufficient. And then we'll do 2. Okay, and so for in I is equal to 0, I is less than or equal to 50, I plus plus. For in D is equal to 0, D is less than. For, okay, so then it's like dp at I at D at 0 becomes dp at I at D at 2, which becomes 0. Okay, so that's initializing it. And now we basically just copy everything in here. I believe it's like basically the same. And then it's just cout res. Okay, cout res at endl. Oh wait, ll res int shift is equal to 1225 basically. Oh, I'll just do 1226. Will you work? dp at 0.length. If this is less than 2560, 2560. Okay, we're gonna submit in C++. Just to see if we can clutch it or not. Pretest 3. Okay, while this happens, I'm going to do if dp at t at d plus delta tag, then we'll do this. How fast? That's kind of tight. I know how to optimize it. If dp at d plus delta at 1 greater than equal to mod, then we just subtract it. We add that and we mod it over here. Okay, equal to 0 ll plus 1 ll. I believe this is like a constant time faster for E1. Yeah, I think I have a rough idea on how to optimize for E2, but I definitely don't have time to implement it. So for now, this is my contest. Let me just make sure it passes. It should be like definitely faster. pretest 18. Oh yeah, that's way faster. Good, good, good. Okay, that's my contest. That's my contest. Okay, I'm going to go over. I might go over solutions, in a little bit. But yeah, other than that, I hope you did well. Bye bye. Let me just check. Okay.